Notre second orateur, c'est Katerina Loannidou. Elle est chercheure au CNRS dans le laboratoire de mécanique et génie civil. Après un doctorat à Zurich, elle effectue un séjour de plusieurs années au MIT avant d'être recrutée au CNRS. Elle modélise des matériaux poreux et amorphes, comme le béton et les argiles, à différentes échelles. L'objectif étant d'améliorer les performances du béton et lui conférer de nouvelles propriétés, comme le stockage d'énergie et de CO2. Un de ces objectifs est donc de réduire l'empreinte environnementale de leur fabrication. Ces travaux, qui sont menés grâce à des outils qui sont issus de la physique statistique, lui valent de recevoir cette année la médaille de bronze du CNRS. Aujourd'hui, elle va nous parler des ciments multifonctionnels pour le stockage de l'énergie. Katerina, tu as la parole pour 25 minutes.
Okay, thank you very much, Sylvie, and thank you also, Sylvie and Daniel, for inviting me. So I'm gonna first describe you a bit more the nanoscale of cement paste and how we can do the modeling at this scale. And then if time permits, I'm gonna go quickly to what we can do with multifunctional cement. I think as Roland mentioned also before, we have a lot of scales that exist inside cement and concrete. Just to make a little distinction, concrete is what we see on the right, is basically a mixture of a binder with a lot of different sizes of aggregates and sand. And the binder is namely the cement, which is the most important phase because it glues everything together. So if we start going down on scales as we move towards the center and left side of the bar, we can see different crystalline phases that develop during the hydration of cement. And also if we go even further down, we can start going into these phases and most importantly into the glue of cement, which is called CSH. This represents calcium silicate hydrates. And they have this ambiguous number because, as Roland was showing before, if we go down to the atomistic scale, we have a lot of different stoichiometric combinations of calcium and silicate that can produce this type of, it's not exactly a molecule, this type of hydrates. And the goal, I'll go straight to the main goal of this talk, is to go from the nano to the meso and try to understand how the cement hydration is happening. So how we start from the cement powder and we arrive at the cement paste. So our approach was based on discrete methods. So we employed a particle-based model. We started from the hypothesis that we have this calcium silicate hydrates organized in a nanoscale particle that we see here on the picture, which is around few nanometers. And the idea was to understand what are the interactions between these hydrates so that then we can produce a larger scale microstructure like we see at the right side. So basically, we use a lot of these particles of polydispersed size, and we were able to reproduce a realistic mesostructure for cement paste that starts from particles of few nanometers and expands up to 0.5 micron. And going up to this size, it allows us to do a comparison with experiments, as I will show you later. And also another reason why we needed to go to such a large system and have so many particles there is because the systems are very heterogeneous and we need to include all these heterogeneities if we want to have a realistic, representative microstructure. So the main route to go from the atomistic scale that contains all the chemistry of the material to the larger scale where we are more interested in the structural elements and the structural organization of the system is to use the potential of mean force. So as we saw before from Roland, this is a free energy approach based on perturbation where basically we define the system that we want to see. So here it's an example for tobermorite in the middle, immersed in water. And then we move these layers of tobermorite in different distances and we compute the free energy. So from the free energy, then we can have the interaction between these particles. So if we try to understand what is the region of cohesion between the CSH particles, we go down to the experiments that Roland explained with the atomic force microscope, that the key finding from there was that it depends a lot on the concentration of calcium ions in the solution. And then if we try to put this in the framework of electrostatics, we see on the left that CSH particles, we can represent them with two charged planes that have actually a high surface charge. And in between, we have the electrolyte with different type of ions, but the most dominant ion is the calcium, which is divalent. So if we go back to theory, we know that DLVO can predict what's happening in these cases, and usually it will predict repulsion. But DLVO is a mean field approach, so basically it has limitation, and its validity stops if we have high surface charges or divalent or trivalent ions, which is the case here for cement. So what's happening in this case? In this case, we have strong correlation forces between the ions that can also induce cohesion. So let's see a little bit more how we can understand better the cohesion in cement. So here I have put three different levels of descriptions. So first, on the left, we have the DLVO, which is a theoretical description. On the other side, we have a full atomistic model where we can perform the potential of mean force calculations. And we have also a description in between, which is lighter from the atomistic model, where we have the primitive model. So there we do the approximation as I was describing before, which is the whole particle is just a charged surface, and we can have basically the ions model as spherical particles with charge. And we have also a solvent, the water here, that at the first approach, we can model it as a dielectric medium with a dielectric constant. So if we go a little bit further, would be to substitute the solvent with the explicit water molecules in this case. And the reason to do this is because with the primitive model, we were getting wrong predictions. So let's go and see a little bit more on this. So basically, I'm gonna, okay, no. Sorry. I'm gonna go back here to the primitive model without the explicit water molecules and the one with explicit water molecules, and show you the result that we get in three cases. So for example, if we look at the gray curve, which is basically the bare ion, we see that we have a repulsive interaction. If we increase the size of the ion because it has a hydration cell, we will see that this repulsion is pushed a bit further. And the reason to do this is because the primitive model accounts for point charges, whereas here we know that the ions have a size because of the hydration cell. But this is not enough to give us, at least qualitatively, the right type of interaction. So then if we move to the green curve, which goes exactly to the primitive model with the explicit solvent, and we model also the water with the SPC model, we see that we have an attraction on the interaction between these two charged surfaces. And actually, on this work that we did with Abey Goyal and Emanuela Delgado from Georgetown University, it was very important to use a good model for water in order to reproduce, in order to get an attractive interaction. So here, again, I'm showing you the case for three different surface charges. The powerful thing of a primitive model is that it's lighter and it's easier to implement. So here, for example, by changing the surface charge, we can also devise interactions for clays that are correctly repulsive. And by increasing the surface charge, we see that in the case of cement, we have a very strong attractive interaction that goes down at a pressure of gigapascal, which is actually what is known from experiments for cement. Coming back to the comment I did before about water, here, what was also very interesting, it was to see the mobility of water in this system. So in this system, in this kind of complex curve here, I want to show you the intermediate scattering function, where basically it's a way to see how particles are moving in time. So we have three cases. The dark blue is the ions, then we have the light blue, which is the bound water, and green, the free water. So we can see that in the case that we have high and low surface charge. So in the case of high surface charge, which is the case of CSH, both the ions and the bound water, which is the hydration cell, they reach a plateau. So they stay correlated for a very long time. So basically, the reason why we have cohesion between cement is because of this correlation of the hydration cells of the water that is around the ions. So this is what is gluing the two surfaces together. And also that's why it was very important on this semi-atomistic approach to use a model for water that gives a very good description of the properties of water. Another way also to understand this and bring it also to a more theoretical model is to compute the electrical permittivity of water in confinement. So basically here I'm showing you in this curve that if we have different ions confined in between two charged surfaces, we see that the value of the dielectric constant deviates from the bulk and actually deviates quite a lot, especially when we are on very small distances. So basically, it's the same way to see the thing. It's basically the very immobile water that is stuck around the ions. It doesn't help the screening of the electrostatic charge, and we have very strong attractive forces between the CSH surfaces. So that was a parenthesis to understand a little bit more on the cohesion of cement. So now that we know a little bit more about this, we want to move to the next scale and start with the two particles, as I was saying earlier, and use different interactions to go to the mesoscale. So the final interaction for cement is a purely an interaction that has an attractive well. But before arriving there, the system goes through attractor-repulsive potentials, as you see here in the figures. So in order to describe these potentials, we have used Lennard-Jones type of potential. So the Lennard-Jones type of potential, we can see it here in the figure. It has basically an energy parameter epsilon and the characteristic distance sigma, where is basically where we also account for the for avoiding the particles to overlap. And we also have the minimum distance, as you see here in the curve, where the force is 0 between the particles. So if we want to introduce also this repulsive solder, we couple this potential together with the Yukawa term. And in order to have this very strong attraction that exists on cement, we have also tweaked the exponents of Lennard-Jones. So instead of having the 612, which is the usual case, we have a 1224. So this makes the interaction well to be more narrow and more sticky. So the way to move forward at the mesoscale model is to use a couple technique of Monte Carlo and molecular dynamics. So basically the difference between these two techniques is in the molecular dynamics, we have a more deterministic approach, which is based on Newton's equation, and we can calculate the full trajectory of the system. So this is kind of the opposite to Monte Carlo, which is a stochastic technique based on random moves. And the goal here is to minimize the energy of the system. So Monte Carlo is very good for obtaining equilibrium properties. Molecular dynamics the same, but we can also get non-equilibrium properties with molecular dynamics, as we can track how the system goes towards equilibrium. So in all the cases, we have used periodic boundary conditions and boxes that contain a lot of particles, so like 10 to the 3 or 10 to the 6 number of particles, depending on the system. So here I'm showing you how the microstructures of these potentials that I showed you before look like in an NVT ensemble. So basically, on the attractor-repulsive interactions that we saw before, there was a repulsive solder. And as we move from the first row to the second row, we have reduced this solder, this repulsion. And we see how the structure looks at the same volume fractions. So we have an initial regime which is made of clusters. So reducing this solder makes the clusters bigger. And then we have a gelation phase, which also, by reducing the solder, we get thicker branches on this gelation. So basically, the interaction is going to determine a lot on the structure of these materials. So, but now let's go back to cement and see how we can put together this information to understand cement hydration, which is basically a transition from a system which is liquid to a stone. Basically, as we say, the system hardens. So here on the cartoon, we see in the beginning the anhydrous cement grains that they have been eventually merged in a water solution. And then we have processes like dissolution of the grains, supersaturation of the solution with the ions, and then eventually precipitation of the cement hydrates. So our idea of modeling this procedure was to place the simulation box in the pore solution where ions are precipitated, are basically dissolving, and eventually cement hydrates are precipitating. So to do so, we use a couple approach of molecular dynamics and Monte Carlo. So we use actually the Monte Carlo in the Grand Canonical ensemble, where we can have precipitation of particles with the probability that you see here that depends on the chemical potential that is basically representing the supersaturation of the solution. And then we couple this precipitation of particles with particle dynamics, molecular dynamics here, so that, and we can devise a kinetic rate that basically tell us how many particles are precipitating over the time that we give to the particles to move, so basically to the structure to relax. So the reason why we came up with this model is because cement is forming very fast within 9 hours. So it's basically a stone that is formed out of equilibrium, doesn't have the time, the system, to relax. So we need to capture both these processes, the precipitation and the out of equilibrium character of this process. So here you can see a video of this simulation and how it looks like. So here we have the precipitation of particles, but you only see lines that connect the centers of the particles. Otherwise, the box will get very busy. And the color code, it shows you how many neighbors the particles have. So initially, we had the phase of clusters that very fast is connecting into a gel structure with elongated branches. And once the system has percolate, precipitation slows down, but nevertheless continues into a densification of the system, and eventually we arrive in a porous solid, like you see here. So here basically it's the same thing we saw on the video on different steps. So we start with the cluster, gel, and further densification of the system. We were able to reproduce the kinetics of this procedure. So you see this at the bottom, where we measure the volume fraction with the time of the simulation, and we have compared it with the degree of hydration that is measured in experiments. So we have this characteristic sigmoid curve with a slow increase in the beginning, a fast accelerating precipitation of the particles, and a slowdown of the procedure later. And here you see how the structures that are out of equilibrium look at the same volume fraction if we change a little bit the repulsive solder of the interactions. So you can see that tiny changes in the interaction of two particles can bring really big changes on the overall microstructure of the system. So basically, the system that we have at the right has been organized in thicker branches compared to the one on the left, and it has also larger pores. We also try to understand and include in the model the heterogeneities that come from the fact that the solution and the availability of the ions in this system is heterogeneous. So there is a gradient of ions in this system that will create also a gradient on the microstructure. So in this model that we did recently, we include basically a gradient of chemical potential that will bring a gradient on the precipitation of particles. And like this, we can get more realistic structures, which are more densely packed close to the boundaries of the boxes, which now they're not periodic in this direction, and they're close to the, basically, they're attached to the grains of anhydrous cement. So once we have devised such a complex model, we want to validate it to see how close we are with experiments. So a first way to validate is to compare porosity. So here we have compared the pore size distribution of this model, where we can see that in the same model, we can capture the gel pores, as they called in cement, which are pores of 1 to 2 nanometers, which is basically the packing between the particles, the gaps between the particles. And then we can also capture the capillary or mesopores with this very extended long tail, as we see here on the red curve, which is actually quite a complex task to achieve from simulations. And on the right, you see how the pores are looking like in this system. So it's only the pores inside the sample you saw before. Of course, the way that we can also get the pore size distribution experimentally is to use physisorption experiments, both with nitrogen and water. We also did a model to be able to compute these processes, that it's a whole total work, and we could talk another half an hour for this. But here I would like just to mention one two key points of this work, which is a combination of density functional theory with molecular dynamics. And there the important thing was to go down to a very fine grid size for the density functional theory, which is a lattice-based approach, and to have realistic interactions for the fluid-fluid and solid-fluid interaction. So then, given the texture that we had for cement, we were able to reproduce the hysteresis for water and nitrogen. So this was, this together with the pore size distribution gave us a confidence that we were able to capture well the pore space, the pore network of cement paste. Another technique that they use a lot to characterize the structure of cement is small angle neutron scattering. So here you see a comparison of experiments in blue and the simulations in red and black. And we were able to also capture this Q⁻³ power law that you see on the scattering, which is again a bit of difficult power law to achieve with simulations, and especially for this very large order of magnitude. So we have it for 1.5 order of magnitudes. And this explained basically through the surface roughness. So the reason why we get this power law is because we have surface roughness at different level at the structure of cement. The very low scale, it comes from particle polydispersity, but as we move to smaller Qs and we look at larger scales in the structure, This comes also from how the particles have aggregate, and they have formed all this rough packing. So that gave us confidence that we have described well the structure of this system. So then we move forward to mechanics, and here you see a validation of the nano-indentation modulus that we computed, and the experimental one that are all gathered on one side. Of course, computationally, we can also compute nano-indentation modulus for lower volume fractions, where we have soft solids, which are not accessible by experiments. That's also one interesting thing from simulation, is that we can also explore phases, the soft phases, when the material is still a soft solid, that usually it's difficult to see from experiments. And a recent result that already Roland showed you is to have also a more close validation from 3D tomography, which is it's a quite challenging experimental technique. So we can see that we have a pretty good agreement on this mesoscale model of cement paste. And I don't know how we're doing in terms of time, so I'll just take 2-3 minutes to tell you what we can do more in terms of application with cement. So our idea came from putting a new phase inside cement, which of course many people have tried to do. So we decided to put porous carbon, as it is an economical compatible phase, and it's a phase also that could bring electron conductive properties on cement. With these electron conductive properties of cement, we could have different applications. So Roland already showed you the freeze thaw resistance that can happen either through to electroconductivity or even without. We can have a Joule effect, which can be used for heating applications, and we can also have energy storage in the form of a supercapacitor. So the way we make these composites, we wanted it to be simple so that can be easily used from the industry. So basically, we use the standard approach that we mix cement and water to incorporate carbon, either in the dry or in the liquid phase. And then we have measured, and we can see that we can get from an insulator that the cement is usually, if we don't have any carbon, into a conductor once we have basically the percolation of the carbon inside the system. And then with the PhD student Ferus to Itié, we are going more into the Joule effect, where with infrared cameras we can characterize and measure the heating of the cement. So basically, this is the type of curves that we get, that we can see a heat up and a characteristic time, which is very short. That's very interesting, that we can heat up several degrees within a few minutes. So here we can see that we can go up to 10 or 20 degrees of heating within really 2-3 minutes. And you can see basically how the heat is propagating from the conductive metals that we put inside through the paste, because the paste is fully conductive. And then the next application is for electrochemical storage, and this is with Sarah and me, a postdoc, and a collaboration with the Sars-Gerald lab in Montpellier. And here, basically, this is our system. We have done 2 electrodes that have a current collector, which is a stainless steel mass, the electrode, which is carbon and cement, and a separator in between, and we immerse the system in an electrolyte. And basically, we have shown through cyclic voltammetry that we have quite a rectangular curve. So it is a supercapacitor, and we can measure capacitance that are basically showing us that we are utilizing all the carbon that is inside the system. And currently we're trying to optimize the systems, because we have some, we are still lagging on the scan rates that we can do. So with this, I would like to thank you for your attention. And I would like to tell a little concrete joke. Thank you.
Merci beaucoup, Katerina, pour ces impressionnantes simulations qui permettent de comprendre les processus de solidification ainsi que les propriétés du ciment. C'était voilà. Est-ce qu'il y a quelques questions? On a le temps de prendre une question éventuellement. Non?
Ah,
Oui.
oui.
Oui. Bonjour, je ne sais pas si c'est à moi que vous pensiez, que vous disiez qu'il y avait une question ou s'il y avait d'autres personnes.
Non, non, oui, allez-y.
Okay. Yes, I'll swap to English because I know there are people in the audience who would rather have the question in English.
No problem.
Thanks for the presentation. So I assume that most of the things we know about the cement mesostructure comes from the characterization of the dry material. And that is not really the case for your nitrogen porosimetry curves that you've shown. And I assume that much of the tomography data that you've shown, as well as Roland, are also concerned with the dry cement.
Yes.
So how confident are you that the structure that you're describing through your liquid phase simulations are to be compared with those that you see in the dry cement? So to put it differently, can you really ignore what is happening during drying? In terms when, like, you can expect that all these mesostructure collapse, right? Perhaps not the capillary pores, but the gel pores for sure.
Yeah. So thank you. That's a very good question. Of course, on the time I had, I couldn't explain everything. We start on the simulations with interactions that are relevant for the early stages of hydration, like the ones I was showing with the attractive well and the repulsive solder. And eventually, as the hydration progresses, the repulsive solder disappears, and we only are left with the Lennard-Jones part of the potential. So basically, we have a process of densification and also changing of the chemical environment that is making the cohesion stronger. So the structure we get through densification, we have done, I don't know how many different simulations. We have at least simulated 3 or 4 different potentials. And the one that will be more relevant for the hardened cement base, this is the one we compare with all the experimental data of the hardened cement base. The other simulations are very interesting, and they could be compared with the rheology data of early stages of when we still have a suspension and a soft gel phase. And this is, we are actually trying to do it now.
Yeah, so is it correct? Do I understand correctly? So then in the end, you're assuming that your structures are hard or stiff enough that they withstand desiccation without deforming significantly?
There are because the attraction between the two, the cohesion, as I was showing, it's at the scale of gigapascal. So we know that we know the shape of the potential, we know the strength is a very deep potential. So, and we have the strength, although it's porous, because of these contacts, it can sustain all the stress of the structure.
Okay.
Yeah, please, Roland, maybe you can reformulate that.
No, to come into the imaging conditions, yes, you're right, absolutely, that that was not done in the TEM environment, so it's super high vacuum. Yes, probably we do have collapse of the thing, but seriously, the water inside the grains or very in between at the very small scale, those are super bound. I mean, you don't get rid of them unless you hit cement. Yeah. So maybe what we hope that we have emptied the capillary pores, right? Part of the gel pores, but certainly not the one inside the hydrate that maintain the cohesion. And the whole idea that Katerina was showing is that the cohesion inside and in between the grains, the same chemistry, same distance is the same. So this water is super. This water that might be there is not going away with the vacuum that is imposed in the TM experiment. If that was your question, right?
Yeah, mostly my question was about how can you be sure that the gel pores that you see, like in the dry cement, are identical to the gel pores that were there before you desiccate? Because the Laplace pressures in nanometer-sized pores are also in the gigapascal range, if I'm not mistaken, right?
You're right. Yeah.
So you can expect these things to collapse, and then like we can only infer what the structure of the wet material was based on the dry. But that's a leap of faith to some extent.
Yeah, so you might have some pores collapsing, but given the heterogeneity of the system, I think what is important here is that statistically we have a good representation of the different pore populations that are there, and overall the connectivity of the system can sustain the mechanical load. So I think it's this more important. Otherwise, for sure, some pores might not be there or disappear after drying. But this is not probably going to change dramatically the distribution of pores. For example, this long tail that we have between gel pores and capillary pores, it might shift a little bit, but it will be there. I think it's more this what is important.
Okay, yeah, thank you very much.
Bien, nous allons interrompre la discussion. Donc, merci à tous les deux, Katerina et Roland, pour vos exposés. Je vous rappelle que donc, tous les webinaires sont enregistrés. Donc, vous pourrez les retrouver très bientôt sur le site de la Fédération Française des Matériaux ou de l'Association Française pour l'Avancement des Sciences. Merci à tous pour votre participation.
Merci beaucoup.
Au revoir.
Merci, au revoir.
Au revoir.